Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. This is module number 23 where we will discuss another type of waveguide which will allow electromagnetic waves to be propagated from one point to another point. In fact, this is such an important waveguide that it actually forms the backbone of the telecom infrastructure, connecting people across continents and providing very high data rates which will be used for various purposes, but this is the only technology today in today's world that can provide very long distance propagation, distances in the order of few thousands of kilometers and at very high data rates, each channel running more than 100 Gbps or at least close to 100 Gbps for a combined data rate of more than terabits per second. So, just to give you a magnitude of what this terabits per second is, if you actually think of 1 gigabyte as the required 1 GB for a non-HD movie, then you can actually fit 1 trillion such movies. It is in fact equivalent of streaming 3 movies per day continuously. So, the global traffic actually runs based on this particular waveguide, and this waveguide is called as optical fiber. Optical fibers you may see outside or you may have seen in pictures. They are very thin strands. If you look deeply into that, these thin strands have 2-3 layers around them. So, there is what is called as an inner layer called as core. Surrounding this core will be a layer called as cladding, and then you have some sort of a coating which is usually a plastic coating or an acrylic coating, and this one is usually embedded in the form of a or inside a jacket. So, this is all that an optical fiber will have. If you look closely at the dimensions, you will be surprised that the dimension here of the core ranges anywhere from say 8 to 100 micron, whereas 8 to 50 micron, 50 micrometers, and the cladding is usually at 125 micron or rather 250 micron, the diameter of that one. The thickness of the coating is somewhere around 100 microns or 125 microns, and the jacket is slightly bigger to give the mechanical strength, but if you, I do not exactly remember the value here, but if you look at the overall optical fiber as you can find from commercial, this would be no more than just about a millimeter or about just about millimeter in width. So, such small dimension, small form factor, very light, and moreover the best thing about this optical fiber is that it is immune to most of the 50 hertz lines that are going around, the power line fluctuations, because this is made out of, the base material is of the fibers is made out of silica, and then you dope, that is you introduce these external atoms into this silica in order to either lower the refractive index or increase the refractive index to form the cladding. And then you coat it, put it into a jacket, and it will actually be a very thin kind of a thing, right. Of course, in practice you do not just take this jacketed optical fiber and then lay them across. You would have seen those optical fiber laying tunnels. You would have a big tunnel in this manner, but this is basically to provide kind of a mechanical protection to this one. So, on top of the tunnel, or the tunnel is usually dug underground, so there could be vehicles moving, animals moving, people moving, there could be construction. So, to protect the fibers inside, you just make out a mechanical tunnel in this manner, and within each that there will be these huge pipes, and huge pipes in turn consist of many such pipes. The exact geometry is dependent on the company which is laying this fiber, and in each of these ducts, right, there will be further cables, again as decided by the company, how much of the fiber they want to lay. And if you look at one strength cable of this optical fiber, the cable actually can contain about 8 and sometimes more than that. Each of this itself consists of multiple optical strands. So, this is kind of a structure inside a structure, but the cable itself will consist of roughly, each duct in the cable itself will consist of about 6 or 8 optical fibers, all jacketed optical fibers with some filler materials or without any filler material. So, this is how mechanical and optical fiber would look like, and of course, as I told you, it is made out of silica, and silica is essentially sand. So, these are basically like thin strand of sand actually, right, and it is amazing that they can actually carry the data rates. The reason why they can carry such high data rates is because they operate at a typical wavelength of 1550 nanometer, okay, and this 1550 nanometer is a sweet spot for silica in the sense that if you were to look at its attenuation, which is measured in alpha whatever dB per kilometer for example, as a function of wavelength, you will see that it actually goes through a minima here at the point 1550. There are additional minima, local minima somewhere else, but this is the point where it actually goes through a minima, and over this region, if you actually look at what is the wavelength at 1550, this will be around 10 to the power 14 hertz, okay, and even if you were to occupy like 10% of this 10 to the power 14 hertz, you are actually potentially dealing with about 10 to the power 12 to 10 to the power 13 hertz of bandwidth available to you, and using this sophisticated communication technology of modulation technology, then you can actually obtain an aggregate data rate of close to 1 terabits per second, okay, which is what recently has been done, and people are moving on to terabit per second kind of a communication. And this is all made possible again in a very simple manner of guiding light through what is called as total internal reflection, right. We have already seen and understood many things about total internal reflection. You could go back and write down the geometric optics approach for this fiber and then try to understand it, but again this geometric optics approach will not tell us what is happening in the cladding, and it will also not tell us the fact that each ray corresponds to a specific electric and magnetic fields, and the way these electric and magnetic fields vary across the fiber, which constitutes a mode, can actually be put to good use, okay. You can encode information, or rather you can put information and modulate information on each of those modes, and these modes can carry information, thus increasing the capacity of the optical fibers, okay. So, we normally identify two types of fibers, the depending on the dimensions as well as the propagation. If a fiber supports only a single mode whose dimension or whose radius is just about 4 micron, the cladding is of course at 60 micron, something like that. So, the total thing is about 125 micron, okay. This is a standardized value. So, if you operate this one at say 1550 nanometer, this will be called as what is called as a single mode fiber, okay, and we use this abbreviation to refer to the single mode fiber as SMF. If you increase while keeping the same wavelength, okay, if you increase the core diameter to roughly 100 micron, okay, then you will see that there will be multiple modes carried by this fiber, and you get what is called as a multi-mode fiber, okay. So, you have a single mode fiber and a multi-mode fiber, and we will not make this assumption that we are dealing with a single mode fiber or multi-mode fiber. We will simply, to understand the mode structure, we will go with what is called as a 2-layer approximation, in which we will have a core. The core has a certain radius a, it is filled homogeneously with the material refractive index n1, and outside is an infinitely long cladding whose refractive index n2 is actually less than n1. Now, in many practical optical fibers, the refractive index profile, so if you plot the refractive index profile down here, you would see something in this manner ideally. So, this would be n2 and this is n1. However, for various applications, the refractive index profile, as we would call it, has also been optimized, okay. You do not of course get this sudden step discontinuity in the refractive index, it is not practically possible. Apart from that one, in order to better adjust the mode properties, you will also grade the profile. So, you will actually see the refractive index profile changing over the cross section in this particular manner, okay. Some specialized optical fibers have a mode structure that would look in this manner, and that would be in this way. There are these what are called as triangular shaped profiles. Then you have profiles with what is called as trench, okay. So, this is one trenched step index fiber. You will also have a trenched but graded index fiber. These different fiber refractive index profiles, which correspond to different types of fibers, are all used at different applications, okay. When you deal with actually in fibers, you deal with a property called as dispersion. Dispersion means that as the pulses propagate, the pulses which carry information, they actually start to elongate or they start to broaden. Sometimes they contract, but in most cases they actually broaden, especially when you propagate over longer distances. And as the pulses broaden, they will start to talk to the other pulses, neighboring pulses, which are also broadening, right. So, in time you are sending one pulse, next pulse, one pulse, next pulse, but if the pulse after propagating certain distance actually becomes broaden, then it kind of one edge of the pulse, the tail of the pulse intersects the head of the next pulse, the tail of next pulse will intersect the head of the next pulse, and so on and so forth, okay, effectively reducing the rate at which you can transmit information. And to deal with the and to moreover, the properties of this dispersion itself is dependent on the type of the mode that is propagating, and therefore it has different values for different modes. Okay. So, these are actually real headaches in fiber optic communication, which of course many smart people are working on it to reduce this one. And to reduce dispersion, we tend to use different types of optimized refractive index profiles of the fiber. Okay. So, that is how you actually get variety of optical fibers suited for very different applications. Okay. However, our analysis will include only what is called a single modes, it will include only what is called a step index profile, which means the refractive index is assumed to be constant, having a value of n1 inside the core, and outside the core, that is in the cladding, will have a value of n2. This is very similar to the optical waveguide that we consider, the slab waveguide. Here in the slab waveguide we took n1 and we took n2 to be less than n1. This is precisely the same scenario in terms of the refractive index profile that we have taken. Unfortunately, the geometry that we have chosen in this fiber is not the same as the planar geometry that we had for the slab waveguide. The geometry in fact is a circle, okay, of course surrounded by this one. This in fact extends all the way along the fiber itself, right. So, this is what the structure would be, and because this distance is quite large, we will assume that this cladding boundary actually goes all the way up to infinity, okay. And this of course is the core, refractive index is n1 here, refractive index outside is n2, and this geometry that we need to consider Maxwell's equation is a cylindrical geometry, right. So, we are dealing with cylindrical geometries, and our equations unfortunately are not simple, and they in fact are little complicated because you are dealing with the cylindrical geometry, but they are well documented. The equations and the simplifications are well documented in the literature. So, hopefully once you get the basic idea of how the light propagates, how to solve for the modes, you can go into greater detail to understand the mode propagation in different types of fibers. Okay. With that, let us begin our modal analysis. We assume core, we have refractive index n1, here we have n2. Now, in cylindrical coordinate system, any point is actually specified by specifying the radial distance r, the angle which it makes with respect to the x axis, which is called as the phi, or the angle phi, and then the height above a certain reference plane. So, if this is my reference xy plane, then the height above this point will be z. Okay. So, you simply imagine the cylinder, cut the cylinder or take the base of the cylinder, and then imagine that any point here can be specified by specifying the radial distance and the angle. So, you drop a perpendicular, you see that line where it connects, and then that would be the angle, and then height over which your point is located would be the z point. Okay. Accordingly, the electric field components will also be ER, E phi and Ez. Only Ez is the rectangular component, and similarly magnetic field components will be HR, H phi and Hz. These all will be functions of R, phi and Z in general. Okay. However, we want propagation along Z axis because we took the fiber and then we take the the height of the cylinder along the Z axis. So, we want propagation along Z, and this means that we are going to assume that all field components are going to look like e power minus j beta z. Okay. So, luckily at least wherever in the Laplacian or in any other equation you get del by del z or del square by del z square terms, you can replace them by minus beta square terms. Okay. We still have a problem with r and phi in the sense that I cannot concentrate only on one particular component. In a cylindrical coordinate system, the way that we are solving, you will have all three of them to be non-zero. So, basically I do not have TE or TM scenario here, although this TE and TM modes exist as a very special condition in optical fibers, which we are probably not going to look at. But in general, just assume that I cannot deal with TE and TM. Okay, rather I have to deal with all 6 components being non-zero, and moreover this R and phi components, whether it is electric field or magnetic field, they actually are tightly coupled, in the sense that I cannot separate the equations, the wave equations separately solve for ER and HR, E phi and H phi, because in the wave equation for ER there will be an E phi term, in the wave equation for HR there will be a H phi term. So, my option luckily is to actually go to the Ez and Hz component and then solve this Helmholtz equation either for Hz or for Ez. Of course, I have to solve it for both, but because both satisfy a similar equation, the form of the solutions will be the same, right. So, I can solve for del square Ez because Ez does not have Er and E phi component coupled into it. Okay. So, you have del square Ez plus k0 square n square Ez must be equal to 0. You can write down a similar equation for Hz as well. Okay. And again, as in the previous slab waveguide case, n can be n1 or n2 depending whether you are dealing in core or cladding. Of course, the method remains the same. I solve the wave equation in the core separately, I solve the wave equation in the cladding separately, and then stitch the two solutions at the boundary by applying the usual boundary conditions of tangential components. Now, do you want to know what the tangential components at this boundary are? Well, you are looking at a boundary, say R equal to A. The tangential components are going to be the E phi component, H phi component, okay, because they will be moving along the interface on both sides, or they will be Ez and Hz components. Okay. So, for if you imagine that you have some kind of a cylinder, then there will also be an Ez and Hz components. I have not shown it in exactly the same way that I have plotted. So, you imagine that this is a cylinder, and as you move along this would be the E phi component, okay, or you move along the cylinder, that would be a Ez component, but it is still parallel to the interface itself. However, the radial component would go from one medium to another medium and actually be perpendicular to this surface, right. So, this would be the R equal to A surface that I am looking at, and clearly this ER component here and ER component on this side, they actually are normal components. So, once we solve for Ez and Hz, we somehow need to solve for E phi and H phi, and this solution of course comes from relating them using Maxwell's equations. Unlike the case of planar waveguides, this relation is quite complicated. So, I will not deal with it, I will leave it for you as an exercise. However, I will go back to this wave equation and then expand this del square out. Okay. In the slab waveguide, this was easily expanded into rectangular coordinate system, but the Laplacian del square in this cylindrical coordinate system is much more complicated. It is in fact 1 by r del by del r times r del by del r, okay, plus 1 by r square del square by del phi square plus del square by del z square. Luckily, del square by del z square can be replaced by minus beta square, but you do not have any such luck for r and phi. Okay. So, you have to go back and put the entire equation here. You write this as 1 by r del by del r del by del r Ez. Okay. So, this is what you are going to get, plus 1 by r square del square Ez by del phi square plus k0 square n1 square minus beta square times Ez equal to 0. Now, this is a complicated equation. I do not want to solve the equation, but I want to make 2 points. Okay. One, if I want propagation inside the core, I better have k0 n1 be greater than beta. Okay. When I take this same equation and apply it to the cladding, I know that in the cladding this fellow will be k0 square n2 square minus beta square, but I want an exponentially decaying solution. So, as I move away from the fiber, my light power should be decaying down. I want all of the light to be confined in the core region itself. Therefore, beta will be greater than k0 n2. So, as long as beta is within these two ranges, of course, the actual value is obtained by applying the equations and then applying the boundary conditions, but as long as beta is there between these two values, you are okay. You have modes which are confined within the core. In fact, if you divide this entire expression by K0 and simply ask for this quantity called beta over K0 to be between these ranges N1 and N2, this beta over K0 is called as N effective, it is called as the effective index of the mode. Okay. And again, as in the case of slab waveguide, you will have multiple solutions, and this time the solutions can be obtained by solving that partial differential equation. There are very many techniques to solve that equation, we will not deal with that, but in terms of phi, your solutions will be of the form e power j nu phi or e power minus j nu phi, where nu is just a integer, at least in this case it will be an integer. Alternatively, you can think of this as cos nu phi and sin nu phi. We will also add some extra theta to this, so that it can be used later on for boundary matching. We will not need it here because we are not solving it, but in general it is a good idea to just take this as e power j nu phi plus theta and adjust the value of theta to obtain different modes. Okay. Theta of course is a constant for a given mode, and you can adjust that value of theta to obtain whether certain mode exists or does not exist. And nu is an integer here for us, because if you move over one rotation, you are moving along e power j nu phi, when you move over one rotation or you perform one rotation, your field values should remain the same, you have come back to the same point, you do not want the field value to just change suddenly there, right. So, that is why we take nu to be an integer. In terms of R, without solving, I will claim that the solutions are going to be j nu kappa R and k nu gamma R, okay, where kappa is usual k0 square n1 square minus beta square under root, and gamma is the usual beta square minus k0 square n2 square. Okay. You can of course even define kappa A as u and then gamma A as w, and then you still have u square plus w square to be equal to v square, where v is called as the v parameter of the fiber. Okay. But what are these j nu and k nu? They are like cosine and like exponentials, meaning that if you look at J0, right, it would actually have a solution which would be in this manner. Right. It looks like a sinusoid, but it is actually a damped sinusoid. Okay. If you look at what would be, I am plotting it as a function of J nu of x, for example, right. So, and this fellow is j nu equal to 0. So, now if you look at what would happen for nu equal to 1, it would look something like this. So, it is little difficult for me to draw, but this is what j1 would look like. So, if I expand it out the equation, then I can write clearly. So, and then this fellow will be on this side and so on. Okay. So, these different functions except for j0, which is actually non-zero at the center, all the other functions, Bessel functions as they are called, they will have 0 at r equal to 0. So, the right solutions for us in the core are these solutions which are of this particular form, damped sinusoidal kind of a form, but they are formally called as Bessel functions of the first kind and order nu. Okay. And k nu are a series of exponential functions. So, you actually have series of exponential functions, all of them going off to 0, but this is how the increasing order nu would look like. That is to say, this would be for nu equal to 0, this is when nu equal to 1, and this is when nu is equal to 2. You can clearly notice that these exponentials are going off to infinity at r equal to 0. So, clearly they cannot be the solutions inside the core, but outside the core they are very good solutions, because you can then match a Bessel function with an exponentially decaying type of function. So, the boundary condition would essentially become something like matching. So, I am again drawing this thing. So, assuming that I am dealing with a fundamental mode which would be of the form of a J0 function. So, you can come up to this part which is A, and then from here take off into the exponential thing. So, this will be k0 of say gamma r, and this fellow will be j0 of kappa r. Okay. So, this fellow is gamma. So, gamma times r. So, at r equal to a, these amplitudes should be equal to each other, and in fact you cannot only deal with expression with just Ez to match to obtain the values of beta. You have to deal with Ez, Hz, Er and E phi and H phi. So, 4 equations will actually give you 4 sets of 4 electric fields and magnetic field components, tangential components at the boundary will give you 4 sets of solutions, okay, and or rather 4 set of equations, and the solution of that turns out to be beta, and we usually denote the solutions as beta nu m, where nu will tell you how the function is varying with respect to azimuthal angle, and then m will tell you how the function is varying with respect to radial. Okay. Under certain approximations, you can go to the general solutions of the fibers are called as He nu m, where H is or EH nu m, where this He stands for hybrid electric modes and EH stands for hybrid electric hybrid modes, which here Ez dominates Hz, here Hz dominates Ez. Only in the special case of nu equal to 0, you are going to get TE0m or TM0m modes, that is you will get the TE and TM modes only when nu is equal to 0. Okay. Apart from this, in general the solutions are He modes, and you may have normally seen these curves. Okay. You can actually generate these curves of what is called as propagation, normalized propagation constant B and the parameter V, and these solutions are actually obtained, I mean the curves that you obtain will actually look something like this. Okay. This would be the curve G11, which is also called as LP01 mode. Okay. This is called as a linearly polarized modes, and these are the actual true modes. So, this is kind of an approximate mode, and these approximate modes are obtained by what is called as weakly guided approximation. Okay. We will not go into details, but this is the mode curve. So, its propagation constant keeps on increasing, and what you observe is that even when V is equal to 0, remember V is inversely proportional to lambda, because V was K0 square root of n1 square minus n2 square times A, and K0 itself is 2 pi by lambda, therefore, V is inversely proportional to lambda or directly proportional to frequency. What this means is that the fundamental mode does not have any cutoff frequency, does not require a minimum frequency to begin propagation, it begins to propagate right at DC value itself. Of course, getting a laser to work at DC is very hard. Lasers usually work when very well when you are in the range of terahertz. So, at which point the B value will be something like this, but if you increase the frequency further keeping all the other parameters constant, you will actually see that as V increases, the allowed value V increases, you are going to see different modes, right. Whereas, you had only one such mode when V was less than or approximately less than 2.405, you get many modes as you move beyond B, right. So, this number V equal to 2.405 is called as the cutoff number, and if your V exceeds this cutoff, only then you will actually start seeing higher order modes. Okay. Those higher order modes could be LP11, LP02 and so on. Okay. We will not deal with these modes, I will instead upload a short presentation for you wherein we have actually solved these equations using a commercial software called COMSOL, and you can see how the modes actually look like. But this is the summary of optical fibers. Optical fibers also guide light, except that light is now guided by this geometry which is in the cylindrical form, and light propagation depends actually in general involves all 6 components, but the fundamental mode is the so called He11 or the LP01 mode. Thank you very much.